Okay, so welcome to our session for today. So now we are going to proceed with the topic cables and arcs. So as we all know, we have an introduction to this that the cables are good in supporting the girders of a hanging structures such as bridges or cable car. So basically, the concept is that we hang the structure through a cable support. So for the arc, it uses the principle of an inverted curve to have more efficient carriage or absorption of the uh, loading. So the principle is a reversed curve to resist our loading. That is for the arc. So cables are practically classified into two. It could be either catenary or parabolic curve. So what will be the difference? Actually, a catenary curve and parabolic curve has only a slight difference in terms of its curve. So basically, if we have a hanged cable wire here, so the loading is only on its own self weight. Okay, so meaning it is free of any other external loadings. Unlike in parabolic, it must have to include sub cables here to carry the load of this deck as well as the girders in it. So that is the difference between catenary and parabolic cables. So what are the principles on treating or analyzing parabolic or a catenary curve? So let us have some principles. So in catenary cables, we consider here an independent cable wherein it carries its own weight. Say its own weight is in terms of W. So if these points are A and B, there will be a corresponding tension at those points. And projecting a horizontal line or a line that connects these two supports, we find or locate the lowest point and then label that as the sag D. Okay, so we also need to determine the horizontal length of the cable. So if this is assumed to be symmetrical, say both or from the lowest point we have an equal dimension x, and then we need to have a horizontal line from this curve for our reference to have the distances of the edges as well as the lowest point. See, I'll just label the highest point y and the lowest point c. That is, both are measured from this blue line here or the horizontal line here. So what will be the formulas that will be involved here? So from the tension, we can say that TA and TB are equal if this is just a symmetrical catenary cable. So we can just equate that into a single variable T. And this T shall be equal to the self-weight of the cable times Y. And then if we need to relate the dimension C and Y, we need also to label our cable length here. Say the curve length is S. From the catenoid equation, we can derive the relationship between X, Y, and S. Just imagine that these three will comprise a right triangle wherein the longest dimension here is Y, okay? And the longest dimension is Y, so therefore this will be the leg of the right triangle. So that is the approach. So meaning this is the hypotenuse and these are the two legs. So we'll just say that y squared is equal to c squared plus s squared. So this is the estimate of our vertical as well as the vertical dimension of c and y from a common reference. So x is also estimated by this expression, c ln of the division of s plus y divided by c. And these are the formulas that will be applicable to catenary cables. Now, what if your catenary cable is unsymmetrical? So this also applies whenever your catenary cable falls under an unsymmetric configuration. So if this happens, we'll just have to change the x's into xa and xb to indicate that these are different distances, and TA and tension B would no longer be equal. So we omit that expression, and still this equation here are also applied. So we'll just have to cut or slice this portion considering the left and the right portion for our tension at A and tension at B. So the same equation will be formed, but we just have to also place our vertical distances at A and B to this common reference line here. So therefore, we form an equation for tension at A. Say this should be Wy of A. And so with this equation, and also with this third expression here. So as we can see, we'll just have to place a subscript for this left portion, which is A. So y becomes YA, S becomes the SA, X becomes XA, and so on and so forth. Similarly, we just write this expression in terms of B. So we'll just say that the tension at B is the self-weight times YB, and YB is this expression. And if you need horizontal distances, this is the expression. Okay, so the basic concept here is just to locate your lowest point. So your lowest point, if it is not symmetric, this x distances is not necessarily equal. However, if it is symmetrical, then this just summarized to x, and we have the same tensile as well as the same vertical distance from these two support. So these are the concepts of catenary cables. So moving on to the parabolic curve. So basically this will carry a distributed load. Say this is the distributed load in terms of W. And then the basic principle is that we are going to locate the lowest point of this cable. So if this is the lowest point, this not necessarily be asymmetrical, but if these two supports are on the same level, this could be a symmetrical one. So we have an asymmetric cable here, so we're gonna label the horizontal distances as x1 and x2. We also need to locate the lowest point from the support vertically. Say this is y1 and this is y2. Then we section the two considering the left and the right portion. So remember, at the lowest point, your slope is 0. So therefore, the component of the cable force at the lowest point is only a horizontal H. So in this support, this is a pin connection. So there will be two reactions vertical and horizontal. So therefore, it will just have a tension that is parallel to this curve. So we also want to get the result of this distributed load here, that is W multiplied by the length, that is x1. Similarly, on the other side, our horizontal force here is also the horizontal force at the lowest point. Okay, but it is oppositely directed. And this as well has a parallel force along the cable equivalent to tensile at point 2. We also express this into its result and treat both independently, meaning we will have an equation for the left side and another equation from the right side. So remember to work with both sides independently. So considering the left portion, notice that there are three forces here. And these three forces comprises of horizontal component, a vertical component, Wx1, and a diagonal force. So therefore, this shall form a force triangle. So we'll just have to apply our force triangle, that we have the distributed load vertical, the horizontal cable reaction at the lowest point H, and it will closed by T1. Similarly, we have H horizontal, this vertical force, and the tension at point 2, which closes to a right triangle. Say this is point 1 and that is point 2. So we'll just employ equilibrium equation. Basically, number 1, we will be having a summation moments equation, taking moments at point 1. We have Wx1 times its moment arm x1 all over 2. That is a clockwise rotation, less h times y1, and that would equate to 0. So solving for h, we have all over 2 y1. And this is actually equal to h. So if we do the same on the other side, we have this expression. So we have already derived the value of h through taking moments at their support. And then from these right triangles established on both sides, we'll just have to apply the Pythagorean theorem, wherein we write T1 squared is equal to quantity Wx1 squared plus h squared. And this shall also apply to the right portion of the cable. So these are the basic relationship that we need to know about these forces T1, H, and Wx1. As for the length of the cable, we have the approximate method and the exact method. And remember that the cable length is expressed in terms of S, say S1 and S2. You just have to apply this formula and this longer formula if we wanted to be exact. And this will be our approach on a parabolic cable carrying a distributed load. How about if we have a cable carrying concentrated load? So that is a different treatment. Say we have here joint A, B, C, and D. Of course, these joints will have a horizontal and vertical reactions as per free body diagram. And we should note that these reactions or resulting reactions shall be parallel or aligned to the cable or the adjacent cable, which is for RA, the adjacent cable is AB, and RD, the adjacent cable is CD. So therefore, they will have to be aligned in a certain single line here, okay, along the slope of AB and along the slope of CD for this RD. And then we apply here moment equilibrium equation considering the whole structure, and then proceed to joint method per joint on the point of application of this loading, say at point B and point C where Q is applied. So we note it in here, joint method at point of application of the loading. So this is just the treatment for a cable that is carrying a concentrated load. So if it so happened that we know the depth of the sag on the lowest point, say we connect both joints by a line and then consider the lowest point, and then we get the distance from that projection, say that is labeled as D, and then we place a fictitious vertical reaction here, say I'm gonna label that as TA and TD for joint D. So when we say fictitious, this is not really the real reaction at A and D. So we will also place a horizontal reaction at A and D. Say we label that as horizontal H. And then we will make a fictitious beam containing the vertical forces. Okay, we label that and then just establish the shear and moment diagram out of this. Say this is the shear diagram. And for the moment diagram, say this is the diagram. Of course, there will be ordinates for M1 and M2, wherein there is a point of application of the pointed loads. So we can derive that out of the areas of your shear diagram as introduced by the procedure of this one. And then out of this, we will look into the highest ordinate of your moment diagram, that is M2, which is actually located at the lowest point, okay? So it is located at the lowest point. It is actually located on C. So M2 is the highest moment on your fictitious moment diagram, and then the location at C, it is located at C where it is the lowest point of the cable. So we can just equate this into a relationship between H, this one, and your M2. And what will be the relationship? We'll just have to say that the moment or the highest moment, which is point 2, will be the product of the horizontal reaction times the depth of sag that is measured from the lowest point up to the projection line of between 2 points, or the point where the reaction is. Okay, so this is the general ruling if we do know this sag distance D. And then we can also get this parallel tensile at point 1 and point 2 by the Pythagorean theorem, saying that T1 squared is equal to TA squared plus H squared. That can be simplified on this expression. Similarly, we do it in the other side. We have this expression. So these are the three key principles in dealing with this cable carrying concentrated loads at certain points. And we can actually appreciate those principles introduced by examples, of course. Okay, so let us consider this cable carrying pointed loads on B and C. So we are tasked to determine tension along CD, tension on segment BC, tension on cable AB, as well as the value of these angles and H, which is indicated in the figure. Okay, so for the first step, we need to start where there is a complete set of, say, given. So if we are going to start with AB, we have a problem on the angle here. So basically, the horizontal and the vertical reactions at A couldn't be determined right away because we still need to determine theta, as well as the tension at BC, wherein the slope is not yet determined, that is beta. Okay, so basically, by the way, there should be a given slope here at CD, and it is actually 345 slope on CD. So looking at the figure, it's obvious that we are going to start from CD. From CD, right, that is a the rightmost portion, and then we are going towards left in order to solve for the remaining unknowns. First and foremost, so what we do, since the distances are given in the problem, we'll just have to take moments at A to come up with the value of the tensile at CD. So of course, this CDX and CDY should be expressed into its slope later on. So we write now the moment equation. We have summation moments at A is equal to 0. We have this one, clockwise moment 8 times 4 less CDX times 2 less CDY times moment arm of 5.5. So you might think that there are two variables here. However, these two components can be expressed into its single unknown CD if we are going to express it in terms of their slope. So from this slope of CD, it is known that the slope is a 3, 4, 5 triangle. We'll just take an angle here referred from the horizontal line and then find what is the function or the trigonometric function appropriate for CDY and CDX. So as we can see, if this is our angle theta, CDY is opposite the angle theta because this is projected on this triangle here that is opposite. Okay, so if we have an opposite component, we'll just use the sine function. We'll just have to see that CDY is equal to CD times sine of theta and CDX as CD times cosine of theta. And then what is the value for sine theta and cosine theta? We refer to the 3, 4, 5 triangle. Say this is our angle theta. So we can see now that sine theta is a 4/5 and cosine theta is 3/5. So we'll just place it in here and then express now your components into this so that we will be having a single unknown CD. Say this is CD times 3/5 and this is CD times 4/5. And we can actually get the value for CD equivalent to 6.79 kilonewton. So knowing our CD, we'll just have to proceed to our joint C by joint method. We construct an X and Y axis and consider here joint C. We place the tension at CD, tension at BC with its angle, and then the downward force here, which is 8. So we take the equilibrium equations along the vertical. We have upward component of 6.79, so that is actually referring to the vertical. So we refer to this vertical slope, we write it there and then divide this by the hypotenuse of your slope. So that is multiplied by 4/5. So this is positive going upwards plus the upward component of BC. So that is actually opposite the angle. So we use here sine function. Then we deduct this downward 8 here and equate it to 0. So we'll be having an equation of BC in terms of beta and a numerical value. So we have TBC sine beta is equal to 2.568 if we are going to transpose all of the constant on the right side. So let this be our equation 1. And then of course we need to perform this one, summation forces x is equal to 0 to supplement our equation 1. Okay, so what are the horizontal forces? Of course 8 has no horizontal force because this is purely vertical. Only these two horizontal, TBC and 6.79. So TBC is a rightward force. So the force component is 3 along the 3 slope. So we write 6.79 times 3/5 minus leftwards TBC times your horizontal is adjacent to your reference angle beta, so that is to be multiplied by cosine of beta. And this shall equate to 0. We then arrange this equation. We have TBC cosine beta is equal to 4.074 and let this be the second equation. So we work with equations 1 and 2. Obviously, we will use our knowledge that the identity sine over cosine is actually equal to tangent, because it is obvious that we have an equation or sine theta, sine beta, and cosine beta on both equations. So therefore, we'll just have to divide equation 1 to that of equation 2. So doing that, we'll be having this one. So TBC here is cancelled. Okay, and then this identity is actually tangent. So we'll come up with an equation of tangent beta is equal to 0.630t, and our angle is 32.2 degrees. So knowing our angle, just have to substitute this angle into either equation 1 or 2 to obtain the value of TBC. So doing that, we will compute TBC to be equal to 4.82 kilo Newton. Okay, so now BC is known. Perhaps you can place it here. So this one is also this one. Okay, so that we can again isolate this joint, draw your x and y axis, and consider joint B. So we note of the loadings here. We have the downwards 3 here. This is TAB inclined at your angle theta, and your 4.82 force here inclined at beta, which is equal to 32.2 degrees. Okay, so we're going to work with this now. So just the same, we write equilibrium equation. So start with y, an upwards TAB times sine theta. Of course, your component here is opposite your reference angle. So we use sine, less the downwards 3 here, less your component of 4.82 along the vertical. Again, that is a cosine function or a sine function. So next is, this is actually equated to 0. So we simplify the equation. We will be having TAB sine theta is equal to 5.56. So again, let this be our first equation. And then we also perform this. So your TAB here is leftwards and adjacent to your reference angle. So we add the rightwards 4.82 times cosine 32.2, and those will be equal to 0. Let this be our second equation. So just the same. Okay, I think we must rearrange it first. So we will be having TAB cosine theta is equal to 4.075, and let that be our second equation. Okay, so working with these two equations, of course, again, we are going to have the identity sine over cosine is equal to tangent theta. So obviously, equation 1 shall be divided by equation 2. Okay, so we do it. This equation is divided by the second equation. TAB is cancelled, and this shall become tangent theta. So solving for theta, we'll come up with an angle of 53.8 degrees. So knowing that we have this angle to be 53.8, okay, we will place it here so that we can now solve for our dimension h. Okay, you'll just have to place here a vertical line, and then of course this is 2 meters and this is our h. So we can take the function of tangent, so it includes these two legs h and 2, so that tangent 53.8 is equal to opposite h over adjacent 2. So therefore we'll come up with the value of h equal to 2.73 meters. So I think this shall complete our solution. So as we can see, the pattern of the solution is just take the whole structure and then proceed with the joint-to-joint method in order to solve for the unknowns. And actually, another unknown is possible unknown here are the reactions at A and D. We can actually use the values here, and then actually the components of AB will be the reaction at A. And same true with the CD, CDX and CDY is actually the reaction RDX and RDY in the problem. Okay, so that's it. And we will have another example on the next video session. So thank you for listening, and God bless.